We'll now take a look at a couple of functions. They're all pretty different from each other, and they all have some characteristics that are worth taking a look at. The first one here is a function that associates the day of the year with the number of hours of sunlight on that day. So the input for this function, which we'll call sunlight, is the date. So sunlight June 22nd equals 15. That tells us that on June 22nd there are 15 hours of sunlight. So the inputs would be the days of the year. The outputs would be numbers that range from a low of 9 to a high of 15, as we'll see. And the rule is that we associate with each day the number of hours of sunlight on that given day. So it would be the number of hours between when the sun rises and when the sun sets. So right now we can see that we're at a high point on June 21st, which is in fact the longest day of the year. And that as we move through the year, you can see that the sunlight function is producing numbers that are lower and lower. We get to September 21st, which is halfway between our high and low point. And on December 21st, we get 9 hours of sunlight. Now, these are rounded, so December 21st will actually be a little bit shorter than December 22nd or December 20th. But we can see that after December 21st, it's going to start rising again as we go into the next year. And then this thing will just keep repeating itself. Now, it might actually vary a little bit, a couple of days here, a couple of days there, because of leap years and some other changes in terms of how long it actually takes the Earth to go around the sun. But the basic idea here is that we have what's called a periodic function because it repeats itself. Now, once again, notice that for each input, there is an output. For each x value, there is a y value. Now, if we were doing this really properly, we wouldn't have a continuous curve here. We would have just a number of dots because we're not saying there's such a thing as April 29 and a half. We're just saying on April 29, there's 13.7 hours of sunlight. On April 30th, one day later, there's 13.8. So really, we shouldn't be connecting them, but it's just a lot easier than plotting 365 points for each year just to have a continuous curve. Now, let's say we put in a second point here, and you'll notice that we have a line segment. And notice, for example, that when we put this at September 21st and this one at March 21st, that we basically have, well, we have a flat line here. The reason is because on March 21st and September 21st, it's on both those days, there are 11.9 hours of sunlight. And what that means is that the net change from March to September is 0 hours of sunlight. And so the average change would be 0 divided by however many days transpire between March 21st and September 21st, which would be a quarter of the year, so it would be about 91 days. So that's why we get a slope here, because we're actually calculating how quickly this is rising or how quickly it's falling. But let's look at when we, let's say, move these 2 points closer together here. And now we're saying from September 7th to September 21st that the slope now is negative 0.05 hours of sunlight per day. That means that over these 14 days between September 7th and September 21st, we are losing, because it's negative, an average of 0.05 or 1/20th of an hour of sunlight each day. That's the average change. Now, if we were to move these points so that they were on an uphill, then you can see that our slope here now becomes positive. The average change over this time period is 0.5 hours of sunlight per day. So as we go from this day where the red point is to the point to where the green point is, we're gaining on average 1/20th of an hour of sunlight per day, which would be about 3 minutes. So each day, we're adding about 3 minutes of sunlight per day. Now, that doesn't mean that's exactly how much we're adding. That's just an average. And so for any two dates, we can see that, let's say, let's set it to June well, let's set it to December 21st and June 21st. And we went from a high of 15 to a low of 9. So over this period of time, which is about 182 days, we're losing on average about 0.03 hours of sunlight per day. So now you can see that in some places, the change is slower than that because the slope, let's say, is only negative 0.1 or 0.1. Meanwhile, down here, where it's steeper, the slope is up to or down to negative 0.5. But on average, between June 21st, which is the peak number of hours of sunlight, and December 21st, so over those about 182 days, we're losing on average 0.03 hours of sunlight per day. Okay, so let's look at another graph here, and this is the distance traveled by someone who drives for an hour at 60 miles per hour and then an hour at 40 miles per hour. So what you can see here is that pretty quickly we have you can see that the slope is a little steeper for the first part of this trip than for the second part, because here we're traveling at 60 miles per hour, here we're traveling at 40 miles per hour. So notice now when we do our second point here, notice that as long as both points are on the steeper part of the curve, our slope is 60 or 60 miles per hour. And what that means is that each hour we're traveling 60 further miles. But now when we put both of our points on the flatter part here, you can see that we're actually have a slope now of 40 miles per hour, and that doesn't change. Now on the last curve, when I move one of the points, the slope is changing. Well, now because we have a straight line, that slope isn't changing. On the other hand, if I, let's say, put this all the way at the beginning and I put this point all the way at the end here, we can see that the slope no longer fits along one of the lines. It's kind of an average of the two in a way. And so what we find here is that over this whole trip, 120 miles, or rather 100 miles in 120 minutes, our average speed, which is represented by the slope of this line here, is 50 miles per hour. Now, as we move this point along here, you can see that our average is moving up because for the first 90 minutes, our average was 53.33 miles per hour because we spent more time traveling at 60 miles per hour than at 40. But again, once we get all the way to the end here, our average is 50 miles per hour. And that's just the slope of this line here from when x is 0, or the number of miles traveled is 0, to, or number of minutes traveled is 0, to when the number of minutes traveled is 120. Okay, so this line here basically says, well, if we traveled 100 miles at 120 minutes, that means that we're traveling at an average of 50 miles per hour. The rate of change of this person's number of miles traveled as compared to the number of minutes traveled is 50. Each, or rather it's per hour. So each hour travels 50 more miles. Okay, now let's look at this strange graph here, which is the plumber's charge. So the way this plumber works is that charge is $40 for the first half hour. That means all the way up to 30 minutes, charge is $40. But as soon as you get a second over 40 minutes, the charge jumps up $40 more to $80, and then it jumps another 40 at 60 minutes, etc. And so because it's the same from 0 to 30 minutes, this is flat. The charge isn't changing. Then it jumps, then it's flat again. Now what you'll notice is that each point, for no matter what the number of minutes worked, there is a charge. So there's no point where we can't get a y value from our graph. For every x value, there's one and only one x value, or y value. As soon as we hit 60, as soon as we get even the slightest bit over 60 at 60.1, it jumps up to 120. So now when we think about adding a second point here, now it gets a little trickier to figure out what this slope means here. So what it's saying right now is when we went from 60 minutes worked to 90 minutes worked, our slope was 1.27. So let's think about what that means. It means that for each additional minute worked, and let's go back as close to 90 as we can get here before we jump down. And you can see right here, the slope is 1.33. So that means that on average, from 60 to 90 minutes, you were paying $1.33 per minute. What is that? Why is that? Well, because $40 increase over a 30-minute time period means that you divide 40 by 30 to get 1.33. So on average, you're paying $1.33 per minute. Now, if you, let's say from the very beginning when the plumber arrived, let's say at 0, and if the plumber works 90 minutes or just under 90 minutes, you're going to pay $1.33 an hour. But as soon as you jump up a little bit, all of a sudden your charge is going up. Now it's up as high as, let's say, $1.72, $1.73. It gets all the way up to $1.78, and that's the slope here. So right now you're paying $1.78 per hour or per minute for each minute that the plumber's there. But again, that changes as we move along this because the slope of our line here is changing. But what we're saying right now is that when the plumber's been there for 100 and let's say 15 minutes, you're paying an average of $1.39 a minute. And again, that's going to change depending on how long the plumber is there and exactly where in the half hour you are. So if you're at the beginning of the half hour, you're going to pay more per minute. At the end of the half hour, you're going to pay less per minute. Because as you can see, the slope of that line, that dashed line, is getting a little bit flatter as we move from the beginning to the end of one of these horizontal steps. Okay, let's look at another one that is showing us the height off the ground of a rider on a Ferris wheel who starts 5 feet off the ground, and the wheel, let's say, is 55 feet has a radius of 55 feet, so its diameter is 110 feet. So the rider goes from a low of 5 feet to a high of 105 feet, and that takes 8 minutes. So to get all the way around to the very beginning again of the Ferris wheel, it takes exactly 16 minutes. And then the second time around, it takes another 16 minutes to get around, etc. And what you can see is that you have a shape that looks sort of like the shape of our sunlight curve. And so what this is saying is that at any point here, if we add our second point, we can say, well, between, let's say, minute 4 and minute 8, that the height off the ground is increasing by the slope of this line here, which is 12.5 feet per minute. Every time we go over 1 minute, we go up 12.5 feet. Over 1, up 12.5 feet. Now you can see that up around here, as we get closer to the top, well, now your height is changing at a slower rate, only 5.24 feet per minute. And the reason is, if you think about your motion on a wheel, more of your motion now is going to be horizontal. Whereas if we are down, let's say, right sort of in the middle here, and we're thinking about how fast we're increasing here, well, right now we're increasing our height off the ground at 19.6 feet per minute. And that's about as fast as we're going to go, because halfway up, our motion is almost purely vertical. Once we get up here, you can see that our height off the ground is changing just by a couple less than 2 feet per minute. And if we move these points like this, you can actually get this value to be just about 0, because in this interval, your height barely changed at all. And in fact, that would be the same if we went from here to here. Your height barely changed, even though you know you're moving. Your height off the ground is back to what it was at the red dot when you get to the blue dot. So your average change in your height off the ground, given by the slope, is about 0 feet per minute, or in this case, 0.07. And so we can always tell how much our height off the ground changed between any 2 points by, or the speed at which it was changing by looking at the slope of this line here. So from the very bottom to the very top here, our height was increasing by an average of 12.5 feet per minute. Now we know that it actually was increasing faster than that right here, where it was closer to just about 20 feet per minute. We know up here, our height, the change in height, slowed down so that it got to just about 0 feet per minute. And so once again, we have a graph where the slope is always changing, and you can tell that by the fact that it's curved. It's not straight anywhere. It may look like it straightens out here, but it's still got a bit of a curve. And this is also a periodic function because it repeats itself. So our height, as you travel around the wheel, your height's going to go up, it's going to go down. The speed at which it changes is also going to change.